Hello everyone, my name is Nitsan Orr, and today I'll be talking about an extension to ISACs that my team and I have been working on. We've been doing real-time 3D mapping, and we're currently working on it, and very excited to tell you about our progress. So, let's start. We've previously heard from Peru that for radiation detection missions, the operator needs to know at least something about the map ahead of time. The area needs to be pre-mapped to some extent. So that takes some data prior to have ahead of time, but that's good if you have it. But what if there's no baseline map to work off of? For example, in indoor radiation mapping, you're unlikely to have a map of the location ahead of time, and it could be dangerous to go in there yourself. For example, in the Fukushima Daiichi meltdown, it even altered the terrain, both outdoors and indoors, which means that even if there were maps, even satellite maps, captured ahead of time, they would not have been good enough by the time this accident happened. And perhaps we want to do detailed close-up inspections of like infrastructure or underside of bridges, looking at pipes or doing other type of preventative maintenance work. All of these would require really detailed and real-time data. So we need real-time mapping when it comes to drones. Going back to ISACs, as you may recall, we have a satellite imagery baseline map, which is okay, it's a good starter, right? We do need to start somewhere, but it has limitations. First of all, it's static, so the second anything changes, it becomes old. It's low detailed, and obviously anything that's not within the satellite view cannot be in the map. So these things are going to stop us from using drones to their full ability. We want these kinds of maps. These are the types of maps that offer rich detail, and they appear wherever we fly. So how do we do that? We would record the map using the drone. We would mount the sensor to the drone, perform SLAM, simultaneous localization and mapping, and then 3D reconstruction to generate a 3D mesh. And then we'll enhance the baseline map in real time with that 3D mesh. So let's talk about the pipeline for such a mapping scheme. On the left, you can see we start with a sensor on the drone. And all the way to the right, we have our goal, which is to get a 3D map into the ISAC's VR interface. Obviously, the sensor will transmit some data. But now the question is, what do we do now between getting the data and getting the map? We need to solve the problem of how do we generate a map and how do we get that map from the drone that's currently flying to a computer on the ground. So first, let's look at our sensor choices. We want a sensor that will offer depth because our map is three-dimensional, and we want color from the sensor. So the map is easy for a human to read and understand. We also want the sensor to work outdoors. So any sensor that works with infrared or IR will get washed out by the sun. Finally, we want a decent amount of range, at least for now. 10 meters is a good starting point. Anything closer, and the drone would have to get pretty close to obstacles before it knew they were even there. So with that in mind, we looked through cameras, we looked through sensors, and we decided to go with the Z2 stereo camera. It matches all those criteria. Next, let's look at the sensor data it can give us. We need input to SLAM and 3D reconstruction. So the type of data that SLAM and 3D reconstruction take are the following: an RGB image, a depth image, an IMU, or inertial measurement unit, and a timestamp. So for each sample, we need to know at what time it was captured. And this data comes quite often. We do need it to be quite frequent, so our SLAM algorithm will work correctly and be able to capture the pose of the drone and the sensor attached. So we're going to go with a 30 hertz rate for now, which I'll explain later how we chose that. Next, we need to decide what to do with the sensor data that we have on board the drone. We need to take some considerations into mind. For example, we want to limit the drone weight and cost. And unfortunately, that means that we don't want and can't put a high-end computer on there. They'll take up a lot of energy or require a big battery or just cost a lot. But unfortunately, SLAM is a high compute algorithm. It takes up a lot of resources. So the question is, what do we do now? Maybe we can make SLAM better. But even if we do make SLAM more efficient and do get it to run on a smaller, cheaper computer, the meshes it produces are still large, and we need to still get them to the ground, to the VR interface. That's not very easy over a wireless connection when these meshes can become hundreds of megabytes. So what do we do? Well, we can notice that our sensor data is looking a bit like a video. If you're looking at the 30 hertz data that's being sent, it's images and it's metadata. So those images are very much like a video. And so we're going to go with a way to transmit videos, which is already tried and proven. And we're going to stream videos from the drone to a more powerful computer that can run our SLAM algorithms and 3D reconstruction algorithms. We're going to go with GStreamer, which is a popular multimedia framework, and it's open source, that can transmit our videos efficiently and in sync. Next, where will this data get sent? It'll get sent to a drone. Sorry, it'll get sent to a computer on the ground, a more powerful remote computer. And that computer, it would be nice if it could communicate with drones. And we do need it to accept sensor data and be able to handle it correctly. So it needs to run task-specific algorithms on it. Well, the great computer for that would be the Isaac server. Now that we have this Isaac server, we're able to run any algorithm we want on it as the data comes in. So our task-specific algorithm for today is going to be SLAM and real-time 3D reconstruction. And how will we do that? Well, with OpenARK, that's a great choice. We chose it because it's open source and because it's built in-house right here at the FHL Vive Center. So that would complete our pipeline for real-time mapping. Let me tell you what happens now once OpenARK returns 3D meshes that it reconstructed. We would send them to the 3D interface for Isaacs. We're extending Isaacs and receiving 3D meshes in real time. We'll use Isaac's sensor visualization code to place the meshes into the map in the correct location and orientation, and we'll be ready to go on mapping missions. So quickly, let me go from the start. We have an onboard sensor, the Z2. The Z2 sends its data over into the drone computer that it's connected to. Then we take that data, we stream it wirelessly using GStreamer to Isaac server. Isaac server runs OpenARK, and OpenARK gives us 3D meshes that we visualize in Isaacs. Next, I'll talk about more details of this pipeline. So, starting with the Z2 sensor. Well, first of all, here it is. It fits in my hand, and you can see on top of it is a gray plastic mount. That mount, you can see that same mount on the bottom picture is attached to our drone. And then we connect the camera through that mount. So the Z2 sensor, we're mounting it on our drone, which happens to be a DJI Matrice 210. And it even has vibration dampeners, which will help us reduce noise in our measurements. The cost of this sensor is about $450. It's a stereo camera, so it creates depth images using 2 cameras. There's no infrared. It has up to 20 meters of depth perception, which is pretty good, and pretty large field of view for its depth, also helpful for us. Its resolution capabilities and frame rates are plenty good for us, since right now we're going with 30 hertz. It's relatively lightweight, so it can fit on even smaller drones than the DJI Matrice 210. And it's got an inertial measurement unit, includes accelerometer, gyroscope, and notably, it comes with a C++ API. So that API, we use it to retrieve sensor samples, the data from it, but it does require an NVIDIA GPU to compute depth images. So since we needed an NVIDIA GPU and we needed an onboard computer that has that GPU, we decided to go with the NVIDIA Jetson Javier NX. It's pretty small, fits on the drone, and relatively cheap. So the way our pipeline works is that we record at 720p at 30 hertz, but then we resize that image to 480p because 480p is compatible with OpenARK, and it's a good balance between quality and performance. Looking at each frame that we get from the sensor, it includes an 8-bit RGB image, includes a 16-bit depth image, and about 13 IMU samples per image because it comes at a much faster rate of 400 hertz, and timestamps for each piece of data in there. And you can see that the megabits per second add up to a few hundred megabits per second. For now, that's fine. But if we increase our frame rate or increase our resolution, those numbers quickly grow. Then we use GStreamer, which is an open source multimedia framework. It has video compression, which is very useful. And ZED even comes with the ZED GStreamer library to create synced up streams with our data. So the data gets transmitted in sync and arrives in sync. Currently, we're using Wi-Fi 6, which will let us test out even higher resolutions and higher frame rates in the near future. And we very much want to try out 5G to be able to do truly remote operations. Now, let's go to the next stages of our pipeline. The Isaac server and OpenARK. Right, so GStreamer sent the data over to Isaac server. Now the streams from GStreamer get decoded. They emulate a connected ZED2 sensor. So OpenARK will be able to see that camera as if it's connected straight to it. We're still working on the ZED2 compatibility with OpenARK. It's a work in progress. And OpenARK, once it's ready to take in data from the ZED2, we'll be doing first SLAM. It combines RGB images with IMU data to calculate the camera pose. And then it computes the 3D mesh using 3D reconstruction, where the camera pose with the depth image and the RGB image are used to create a textured mesh, which grows in real time as more data comes in. And those mesh results are sent continuously to the Isaac's VR interface. Now for the Isaac's interface, we're hoping to get images like these, where on a 2D screen, they look pretty good, but wearing a VR headset with stereoscopic depth perception, it feels very immersive. And if this was a camera mounted on a drone, and you were looking from the drone's perspective, you would have a pretty good understanding of where you can fly and where there are obstacles. So on our Isaac's interface, first of all, as you probably heard, it runs on a VR compatible computer. And we're still working on the OpenARK mesh visualization. But when we do it, the Isaac's visualization script will be of great help to us. It just converts incoming meshes into virtual reality objects. Then the origin of the mesh is transformed to the drone's position and orientation. That way the mesh gets rendered in the right location, in the right orientation. And we see the mesh show up. And of course, we can use all the great tools of Isaac's, including rotation, rotating the map, translating the map, zooming in and out. So some possibilities with real-time data. Well, we can enable first-person view, enabling depth perception for the operator, or in other words, telepresence. Imagine being a firefighter, and instead of you being out in the field, you're controlling a drone and you're seeing a first-person view from that drone's camera. You can put out fires with the water hose connected to a drone, and you're able to reach many high locations. You're able to spray water from different angles while staying relatively safe. We're also thinking about multi-drone mapping missions. For example, we can inspect imports coming in by ship. We can inspect them for radioactive material, for example. And we'll have multiple drones acting in different roles. Some will be mapping the environment. Some will be inspecting the cargo ships for radiation or any other data. And we can also use multiple drones to do faster mapping simultaneously. And that's a great use for the Isaac server, where multiple drones sending their sensor data, raw sensor data, can be combined into a global map and transmitted back to the Isaac's interface. With that, I'd like to say thank you, and I'm happy to answer any questions.